That's probably the most important one, you know? It's gonna get harder as we get to you guys, so be studying it.
Yeah, wait.
You can find another one. Alright, that's probably the most important one that we're looking at for this whole process, although this one's important too, the gears on the chain. But I had drawn it without any gears, so before my first model, this was the most important spot. So, Emily, what do we see? What pairs do we see?
The force of the tire on the ground.
Right, tire on
Force
ground.
of ground on tire.
Yes, you got it. And force
That's just-
of ground on tire. So once you get one, you just switch them and you got the other. All right, evidence, Emily?
The ground is pushing up on the tire, I guess. I guess the wheel kind of bends a little bit.
All
Or
right,
maybe that's
this
the
is
other way.
take a really hard look here, because this one is why the bike works right there. And the force of the tire on the ground is, you can actually, there's a gripping, right? There's this force, and you can even see like little stones or pieces of gravel flying backwards. So you can see that force of the bike on the ground. But then, amazingly, the most important part of this whole process, you found it, is the ground pushes back on the tire and it moves the bike. So that's the important one right there. So, you see another one, less important but still present?
Well, maybe, I don't know if it's right, but the hands on the handlebars.
Yes.
Hey.
Okay.
Let's
Force
go.
of hand on, what's that called? Handlebar?
Handlebar.
Handle, grip, whatever. And what's the other one?
And force the handlebar on hand.
Yeah. All right. And the evidence is similar to what we have seen, so. All right. Can you come up with one more? What?
Spokes on wheel.
Okay,
and wheel
spokes
on
on wheel. Okay.
And the evidence would be that when you're riding the bike, the wheels aren't collapsing, so the spokes are
Right.
pushing them out, and then for the other way, you're gonna see an indent in the tire.
All right. Very good. So, action reaction taking place all over the place, all over our environment.
So without
Anytime.
this,
Pardon?
without this law,
Yeah.
nothing would really be able to push against each other because there would be no force working against other forces.
That's right. In fact, for the longest time, in our ignorance as human beings, we thought that when we got into outer space, since there was no atmosphere, there was nothing to push off of, that we thought that our rockets would not be able to accelerate. Like say they were in a holding pattern, you want to accelerate it, we didn't think that it would work. But we were thinking about Newton's law because as particles spew out of the rocket in the combustion or whatever, their force, the force out of the rocket is the action. What's the reaction? Is the rocket goes forward. It wasn't that we were pushing off of anything. It was this all the time. So when we get up into space, can we accelerate? We can. So pretty interesting. All right, let's talk about just a few more notes on Newton's third law. This pretty clarifies a lot of it. But let's review that one point from yesterday. When they're equal and opposite. We go here to this one. If the force is this way and the action and reaction is that way, why do they not just cancel each other out and the bike never moves? The same question yesterday. I thought we were going to be stuck in here for the rest of our lives because the door would never open. So also the equal and opposite forces. Do you remember what the answer was to that, Emily? One?
Well, like in the case of the door, you said it wasn't actually pushing on the other side of the door. It was like when you apply force to the door, it's like
Right, right. The door was pushing on me and I'm pushing on the door. It wasn't like I was pushing on the door and some force was also pushing on the door. It was two different objects involved. Same thing, see, it says on the ground, on the tire. They're on two different objects, so they're equal and opposite, but they're not counterbalancing each other. All right, so let's look at the last kind of scenario, and that is whenever there's a force, there is an acceleration. Force equals ma. So recall that. Wherever there's a force, there is an acceleration. So, and it's related proportionally by the mass. So I am going to drop this ball. Can you see it accelerate? Can you see it go faster and
You
faster?
can rewind it.
We have to slow motion it. Probably not, but you are well convinced that it's accelerating toward the Earth. It's going faster and faster at the acceleration of 9.8 meters per second every second downward. So if we dropped it out the window, which we're wont to do sometimes, it goes. You might be able to even see it go faster and faster. So, the point is, I'm seeing an acceleration, so there must be a force. I don't see anything touching it, so it's a non-contact force, but what force is it? Of course, what's the force pulling it downward at a faster and faster pace? Gravity. So, we have an action right away. We have gravity as a force, so the force of gravity has to have, so say we're going to drop a ball. So on your notes, drop a ball. Right there is an acceleration. So there is a force due to gravity. It's a little trickier now because gravity is a non-contact force. It's not something where we're touching the door and the door is touching us, but we're seeing it, we see the effects of the acceleration, so we know that there's a force. Where is the equal and opposite force? In that case, where is the equal and opposite force? Well, that's the question. So we have the action. The ball is being pulled by the force of gravity. Where is the reaction? Well, we've been trained, well taught.